Good morning, everyone. Myself, Dr. Ambuj Kumar Kushwaha. Currently, I am working as an assistant professor in Janta Vedic College, Badot. Today, we are going to study about a very interesting and important topic, that is infrared spectroscopy. Infrared spectroscopy is a type of spectroscopy. That means spectroscopy is used for the detection of structures of any chemical compound. Like the H1 NMR is used for the detection of type of hydrogen. C13 NMR is used for the detection of type of carbon. Similarly, IR spectroscopy is used to find what type of functional groups is present in the structure. The IR spectroscopy in IR spectroscopy, we use IR radiations which causes vibrations in the molecules. The IR region is present between the visible region and the microwave region of the electromagnetic spectrum. This IR radiation is further divided into three parts. That is near IR region, which ranges from 14,000 to 400 centimeter inwards, and very less number of organic compounds absorbed in this region. Next is mid-IR region, which ranges from 4,000 to 700 centimeter inwards, and most of the functional groups absorb in this mid-IR regions. Next is far IR region, which ranges from 400 to almost around 0 to 10 centimeter inwards, and almost none of the molecule are absorbed in the far IR regions. The principle of IR spectroscopy. In IR spectroscopy, we irradiate infrared radiation on a molecule which causes vibrations in the molecules or the bonds. When the applied frequency of the infrared radiation matches the theoretical or the natural frequency of the bond, this IR applied IR region is absorbed in a molecule and a peak is absorbed. For the absorption of the IR region, the most important part is that there should be a change in the dipole moment of the molecule. Now, where the absorption will occur means at what frequency this absorption will occur. It is governed by the Hooke's law. Hooke's law states that the frequency of the absorption bond band is equal to 1 by 2 pi root over k by mu, where k is the force constant, which is the measure of the bond strength. That means if the bond strength is higher, then the frequency will be higher. Like the triple bond is of higher frequency than the double bond, and it is of higher frequency than the single bond. Whereas mu is the reduced mass, which which means that higher atomic mass molecules absorbs at lower frequencies. After looking at the at what position the bond will appear, the intensity will appear. Now we will measure at what bond, what is the band intensity, means at what height or what will be the height of the band intensity. It depends upon the three factors. First is the change in the dipole moment. As we can see that greater the dipole moment change, greater will be the intensity of the bond. Next is electronegativity difference. Higher the electronegativity difference, higher will be the bond strength. Like in OH, NH, and CH, the OH, the bond electronegativity difference in the OH is much higher than the NH as compared to CH. Hence, the intensity of the band in OH will be greater than NH, and it will be greater than the CH. The next is concentration. If we make the solution of higher concentration, we will get a more intense peak. Now this IR spectrum is divided into two parts. The first is functional group regions. In the functional group regions, the absorption of all the functional groups occur, and it ranges from 4,000 to around 1500 centimeter inwards. And the next is fingerprint region, which ranges from 1500 to 700 centimeter inverse. And this fingerprint region is unique for all the molecules, means one molecule will have a single fingerprint region which will vary with the other molecules. Like in human being, every human being have its identity of fingerprint. This molecular vibrations in IR spectroscopy is divided into two parts. First is stretching vibrations. In stretching vibrations, only the distance between the atom changes and the bond angle remain constants. And this stretching vibration occurs at a higher energy as compared to the next which the bending vibrations. Next comes the bending vibrations where the bond angle changes and the bond distance remains constant, and it occurs at a lower frequency. The stretching vibration is further divided into two parts, the symmetrical stretching and the asymmetrical stretching. In symmetrical stretching, the bond angle does not change as we have seen in the stretching vibration, but both the bond angle either is stretched or is contracted in the same direction, whereas in asymmetric stretching one bond is stretched and one bond is contracted. The bending vibration is further divided into two parts. First is in the plane vibration. In the plane vibration means the bond angle changes in the same plane. The plane of the molecule or the bond is not changed. It is of two types. Scissoring. In scissoring, both the molecules, both the bonds either come towards each other or goes away from each other. Whereas in rocking, both the bond angle changes in the same direction. Either goes to the right or goes to the left. Out of the plane vibration, in this the bond changes its plane, like we see in wagging, the bond is going either out of the plane or inside the plane, so the bond plane changes. Whereas in twisting, one bond is coming out of the plane and the other bond is going inside the plane. Now we see that what type of functional groups will carry which type of frequency, or what frequency will be absorbed by which functional group. Like in CH stretching, it comes around 3000 centimeter inverse. In alkene it comes around 1700 centimeter inverse. Similarly in amine it comes around 3500 centimeter inverse. Now we will see what factors are affecting this vibrational frequency. As we have seen earlier, the bond order. As the bond order increases, that is, if the strength of the bond increases, the molecule will show absorption in higher frequency. The second is electronic effect. Electronic effect means resonance or inductive effect. If the bond order or the bond strength increases by any resonance or inductive effect, then the frequency will increase. And if the bond order or the bond strength decreases by the electronic effect, then the frequency will be decreased. Next is hydrogen bonding. Wherever a hydrogen bonding is present in a molecule, it will lower the frequency of the bond. Next is ring strength. As the size of the ring decreases, the frequency of the molecule also decreases. Now, are the some of the applications of IR spectroscopy. The IR spectroscopy can be used to determine the functional group of the molecule. It can also be used to determine the purity of the compound, how pure our compound is. It can also be used for reaction monitoring to see whether our reaction is completed or not. And finally, it can be used to separate the isomers of any molecule. Thank you.